Доброго вечора, ми з України. Here I'll present this Solar MPPT device which I designed. It's cheap, simple and efficient, unlike claimed MPPT you can buy on internet like these ones. I'll show the difference later. I explained the basics and what you need to know to evaluate the efficiency for your particular use case and decide whether you need an MPPT at all. So here will be a simplified theory, then explanation of problems with alternatives, then details about how to assemble and program this device. So the theory basics. First you need to consider is that there are two different efficiency factors for solar controllers: generation efficiency and conversion efficiency. This chart represents solar volt-ampere characteristics. It scales depending on solar panel size and amount of light. We will only consider more or less evenly lit panel, no hard shadows, as this device targets small to medium-sized solar panels, for example, for hiking. Here are OCV, open circuit voltage, and MPP, maximum power point. MPP is always around 80 to 81% of OCV. It doesn't depend on amount of solar energy nor on panel temperature, while actually solar panel efficiency rate depends on its temperature. Lower temp is better. MPP rating always refers best conditions and likely won't be achieved by real users, so expect to receive some like 10% less in a good case. If you place panel in non-optimal angle, you will receive less. If you place it behind some window, you will also get around 30 to 50% less. Now about voltage specifications. There can be confusions with voltage in product descriptions. There is often referred to system voltage, which means a voltage of a battery being charged. So it can be typically like 12 volt system, 18 volt MPP, and 22 volt OCV. I've drawn this chart to show voltage from different perspective. This is for charging lithium-ion directly with MPPT and 6 volt MPP rated panel. It shows the real voltage ranges for both battery and solar panel depending on conditions. Real MPP will be from around 4.5 to 6 volts. For optimal work, this range should be slightly above the maximum battery voltage, which is 4.2 volts for lithium-ion battery, so it doesn't overlap. This way you won't miss MPP in any condition. MPPT device converts excessive voltage to extra current in a respective proportion with correction for DC-DC conversion efficiency, which means that typically this is your target voltage, like V battery, and there is some excessive voltage above it to MPP, which flows somewhere here depending on amount of light and temperature of panel. And you convert this excessive voltage, like let's say 30% to 30% more current, and obviously you will lose some during conversion. The generation efficiency depends on how close you are to the MPP. Consider it 100% use of a solar panel in its physical conditions when voltage stabilizes at MPP. If you connect panel when current MPP is 18 volt directly to a 12 volt panel, voltage stabilizes at 12 volts somewhere here instead of potential 18 volts, and you get 12 divided by 18, which is around 67% generation. In this case, the theoretical maximum advantage of using MPPT is the opposite, 18 divided by 12, which is 1.5, which is like 50% improvement. Additional corrections are, on lower voltages, there will be actually slightly higher current, up to some 5%, so instead of 50%, it's like rather 45% improvement. And then by fact, with 18 volt rated panel, you won't likely receive 18 volt MPP and rather 16.5 or something, as it would require cooling. Solar heats up and drops voltage by some 7 to 10%. And correction for conversion efficiency of DC-DC buck converter. That will take away some 5 to 10% more. I'll explain in next chart. Realistically, with correctly designed system, you can expect an MPPT device benefit of around 25 to 20 to 25% comparing to direct connection. The more distant the battery voltage from MPP voltage, the more benefit to the more benefit from MPPT, as you can see from this chart. So you convert this excessive voltage to extra current. But for overall best efficiency, it should be close. These ranges should be close. If you connect solar to a battery via plain DC-DC buck converter, it will work pretty much like direct connection, but ensure that battery voltage won't exceed the specified limit. Solar PWM controllers work similarly too. They drop solar panel voltage to a level of battery voltage. Now briefly about the DC-DC conversion efficiency. This typical chart of such buck converter. Here are four curves. Here are four curves with different input and output voltages. These plus comments emphasize what factors improve conversion efficiency. Higher output voltage improves efficiency due to less percentage of loss on reverse phase diode. Lower input to output ratio improves efficiency due to shorter reverse phase when current flows through the diode. Efficiency on small currents is highly affected by self-consumption of device. When your output is some power bank, which has its own BMS, there will be additional internal losses from some 5 to 25%, which is a lot. So for efficient solar power bank, this design needs to be custom, and you need to charge a battery directly without excessive BMS that is oriented for USB input, like with this device. This newest prototype, it has SMD power MOSFETs, which are very good. I can recommend it. This latest prototype is apparently the most efficient solar power bank charger in the world at the moment. It charges a lithium-ion battery directly with 90+% conversion efficiency, uses no shunts, no input, no output diodes, and still doesn't have reverse current. This is achieved via a special trick based on OCV measuring. That feature was recently added to the project. Overall, it's around 60% more efficient than this particular claimed MPPT lithium-ion charger, and I tested this. I want to make a separate video about it to tell more. If you don't have reverse current protection, real reverse current in panel when it's dark is very small according to my test. For 18 volt 50 watts panel, it was 2 milliamps from 12 volt battery flowing to solar panel. Now about incorrect work of this claimed MPPT device, and it's also claimed in its datasheet of this chip. It just works as a plain buck converter and drops 18 volt panel voltage to 5 volt output, resulting in somewhat like 30% generation when we're talking about 18 volt. I'll connect this to my device first. Connect solar to my device first to show how it should work. So, established. For 5 volts, we have stable conditions. We now have 360 milliamps with proper MPPT. MPP stabilized at its precision of voltmeter and ampermeter with separate power source. So MPP stabilized at 14.84. You have 120 milliamps and input dropped to 4.6 volts, roughly like output. So it just drops voltage. It's simple buck converter. It doesn't have any tracking. And further is even worse. So we connected to QC port. It attempts to perform handshake. It fails to raise voltage and everything reboots, and during this phase voltage flows here and there, and you cannot, not fast enough to track it, but you don't even generate power in a lot of time. So it just doesn't work with QC, and I assume same would happen with a lot of QC ports. Now about other alternatives. I've seen some devices reviewed on internet that have an MPPT configured resistor. Actually, this one is based on such a chip, which actually configures tracking a fixed input voltage. It's not an MPPT, they just claim it to be MPPT, which would work very bad. You either configure it lower for lower voltage and lose much, or you configure it for high voltage and can lose much more. I'll also refer a video of Great Scott, link in description, in which he assembled an MPPT based on both MPPT chip. I think it's also actually the same chip. And it resulted in poor efficiency, while he was only testing the conversion efficiency. There is also apparent fixed input voltage tracking according to divider and the reference voltage that he mentioned, so the chip works bad too. Some sellers may mark some simple DC-DC buck converters as MPPT and specify the chip it uses, while the datasheet of that chip doesn't even mention any MPPT. According to all I have seen, it appears that for low mid-power up to some 100 watts, there is just no correctly working MPPT devices you can buy. There are videos on YouTube when people DIY MPPT devices based on Arduino with canonical implementation with some current sensors. Those actually should work. So does my device, but comparing to versions based on Arduino, my device is cheaper, simpler, smaller, and works better in a lower power range, partly because much lower self-consumption. It's open source, the link to GitHub is in description. There is code, compiled firmware, documentation, extended documentation is in source code file header, images of schematics, and this very prototype with extra comments. For programming PIC12F675, you can use a DIY programmer on Arduino, for which I've made a modification to minimize it to this, like several components with additional to Arduino, and PIC was marked to this side. This is complete programmer. See link to GitHub in description. You can and should use also protection resistors. It's all commented on GitHub. Why I use this particular MCU? Because it's cheap and available in Ukraine. You can easily buy it. During studying and implementing this, I realized that standard hardware PWM implementation has disadvantages, especially if you want to drive inductor in continuous mode. Most of modes here are harmonic, non-interruptible, high-frequency PWM with smooth stepping, yet working on low-frequency MCU as implemented in hardcore assembly, along with handling limiting logic and input voltage monitoring at high frequency. Now some PCB notes. Here are main parts, this main part with inductor and diode on the opposite side. It was just more comfortable to assemble this way. Then the feedback part. This is feedback part to stabilize voltage. To limit output voltage. 2 voltage configurators for and selection switch. I just use it for comfort. Dense layout of output buck converter circuits. Short power lines. There is path for current to flow through capacitors. These are output capacitors, and current flows exactly through this. They are not somewhere aside. So that for capacitors, the in and out lines are separate. This exact prototype is fine for a 50 watt 18 volt panel for 12 volt 4 amps output-ish. Inductor is the limiter here, because it's 5 amps rated, and I actually have no idea where you can find power inductors in Ukraine. For higher currents, there should be stronger inductor and radiator on MOSFETs. Note that after reaching inductor's limit, you can still receive bigger current, but it will work inefficiently and stress other components. Some extra notes on power banks with power delivery and this stuff. Such power banks may not want to consume energy without handshake and act pretty weird. I tested several different power banks and had really different results. This one with QC works, which is very comfortable for me. It works fine without handshakes. You can actually feed it with pretty much any allowed voltage and it will just accept it. So for such usage, I mean, when you want to charge power bank, complete power bank, a particular hardware combination needs to be tested. And it's not only related to my device, other existing converters have such problems too. There's some problems with different combinations, and you need to consider that. A few more words about this device. It uses CN3791 chip and it tracks fixed input voltage of 12.3 volts defined by this voltage divider of these two resistors. So its generation efficiency is pretty low, like some 75%, and its tested conversion efficiency is also low, around 77% in my tests. It's also suffered because of extra diodes, Schottky diodes they put to avoid reverse current, which isn't good for reverse current protection, by the way. And for such protection, it's better to use MOSFET with certain connection and some mechanism to define when to open or close it. It's properly implemented in this prototype I mentioned, and you can find schematics and explanation in GitHub repository. You can find this very image I'm showing right now. So this video is already pretty long, and I think that's it for now. So thank you for watching.